Hello everyone, I'm going to present my work on large-scale flood risk modeling, and it is about the floodplain storage and hydrodynamic interaction in flood risk estimation. And what I mean by hydrodynamic interaction is how much the floodplain storage due to inundation, overtopping, or a dike breach at the upstream part of the catchment is affecting the propagation of the wave and reducing the inundation at the downstream part of the catchment. So the objective of this study is to develop 1D continuous hydrodynamic routing scheme and compare it to the old routing scheme, which is the piecewise, and to investigate how much this change is going to affect increasing or reducing risk estimation in the catchment. This work is being done as a part of original flood model chain RFM, and it contains 5 models starting from weather generator, hydrological rainfall runoff model, then hydrodynamic 1D 2D regional inundation model REM, and the last part of the model chain is FLEMO, and it is a flood loss model. So the focus of the study mainly on the regional inundation model, and it results in a new version of the model. And to introduce the new model, I have to explain the old version of the model. So the old version of the model RIM1 uses a piecewise routing scheme where there is a boundary condition at the beginning of each subbasin, and this actually prevents the model from passing any inundation information from the upstream of the river to the downstream. While in the opposite side, in RIM2, it uses a continuous routing scheme where there is only boundary condition at the very beginning of the river, and this actually allows the model to pass the inundation information from any upstream subbasin to the downstream. To validate our study, we use the Rhine catchment with an area of almost 185,000 square kilometers and more than 1,200 kilometers of river network. To analyze the newly implemented methods in the RFM model chain in terms of hazard, we compare the simulated discharge and water level with the observed data, and in terms of risk, we use the occurrence exceedance probability and expected annual damage to compare the estimated damage and risk calculated by both models. For the water level calibration, the performance of REM2 ranges between 0.83 and 0.15 meter based on mean absolute error, and ranges between 0.35 overestimation to 0.65 underestimation based on mean bias error. The next comparison between both models is based on the total inundation volume and the inundation area in the whole catchment. So the difference between both models is very clear, with both models capturing the main events, and REM1 simulates a large number of small events. And taking into consideration that the dike system in the Rhine is designed for 200-year return period, simulation of volume and inundation area by REM2 seems more realistic, and that's because of the reduction in the inundation area and volume result in REM2 when inundation happens at the upstream, and this interaction does not exist in REM1. And to analyze the difference between the overtopping result from both models, we can take a look on the highest flood events along the Moser River and the downstream part of the Rhine. The left y-axis shows the maximum simulated water level by both models at each location along the river, and the right y-axis shows the difference between simulated water levels by both models, and the overtopping size is represented by the size of the bubble in million cubic meter, and we can see that the overtopping by REM2 gets smaller towards the downstream, while the overtopping by REM1 is not affected, and that's because of the updated boundary conditions in REM1 from the rainfall runoff model that does not have the information of the inundation at the upstream part of the river, and that's what the continuous routing in REM2 considers. So if we take a look at the highest event on a spatial scale, this slide shows the spatial difference between both models, and not only REM1 overestimate inundation area, but it also overestimate inundation depths, as the information about the inundation at the upstream is not passed to the downstream, and that's because of the updated boundary condition from the rainfall runoff model. So the upstream part of the river is kind of disconnected from the downstream part of the river, and it doesn't know that some of the water has already been taken out of the river and caused inundation at the upstream, and that's why it overestimates the amount of water that reaches downstream. In terms of damage, all damage models predict less damage for REM 2 than for REM 1, and that's because of the smaller inundation extent and inundation depths. And for the 100-year event, the total damage estimated by REM 2 is almost 2 billion, while for REM 1 is almost 3 billion, while the reported damage for the 1993 event is 1.2 billion, which is much closer to the estimated value by REM 2 than by REM 1. And the expected annual damage for REM 2 is more than half the estimated by REM 1. To analyze the impact of the hydrodynamic interactions, especially on the estimated damage and risk, we subdivide the river network into different segments based on the location of major cities and confluences. And then the estimated damage by both models is aggregated and used to derive risk curves for each segment. At the upstream segments 1, 7, and partially 10, the risk curves by REM 2 are higher than REM 1 curves, which indicates higher loss produced by REM 2. Further downstream, the risk curves converge at segment 2 and segment 3. At lower part of the Rhine, segment 4, 5, and 6, the modeled risk by REM 1 consistently exceeds the estimated by REM 2. In these segments, extended floodplains and high exposure is expected, and there is a strong potential for widespread inundation and high losses. And we can see that REM 1 systematically overestimate overtopping and hence generate much higher damage compared to REM 2. This slide shows the spatial distribution of inundation areas and damage for two large events simulated by both models. The values are aggregated for sub-areas, and the color grade represents the absolute value of maximum damage and maximum inundation, while the bars represent the share of each model from the absolute value. For both events, inundation area and damage simulated by REM 1 dominates the lower Rhine, while in event 2, REM 2 does not affect the lower Rhine at all, and that's because of the interactions considered in REM 2 and not considered in REM 1. As a conclusion of the study, the continuous routing approach leads to smaller inundation, and the resulting expected annual damage is more than halved. So the improved hydrodynamic routing scheme will promote better risk estimation in the national scale.